This is a short video about robot control. Here we would learn how to use gradient descent method to control a robot to move to an assigned target. This video will be broken down into the following sections. 1. Gradient descent algorithm. 2. Building the robot. 3. Setting up the environment for the testing. 4. Set up the loop for the animation. 5. Set up the while loop to update the angles until the robot arm gets to the target. 6. Test the result. Without wasting more time, let's get started. Section 1. First, we will program a gradient descent algorithm. This takes a scalar function of multiple variables. That is a function that takes a vector input but returns a scalar value. And the vector input at which the gradient of the function is to be computed. Section 2. The robot would be created to inherit from the handle class, so that we can change its properties without having to return the class to a new variable. As you can already tell, we are using object-oriented programming paradigm here. This robot object will have 7 properties. 5 of these properties will be private since we don't need to use them outside the robot. Lengths, points, members, joints, and pins for aesthetics. The other 2 properties are function handles that would be used to compute its current state and update its position for animation. So we name them as such. Compute and update. Now let's move to the methods. We have 3 methods, one public, obviously the constructor that makes the robot. And the other 2 are compute and update. As you can guess right, the compute is exposed via the handle compute and the update is exposed via the handle update. Since the update and compute properties would be connected to the update and compute methods respectively, we create the private methods first and then we create the constructor. Section 3. Now we set up the environment. We define the figure and its properties like color and position. We define the axis and apply the hold-on so that we can add multiple graphic objects to the same axis. We create a learning rate text LRTXT handle that is used to display the current learning rate. Then we add a slider U control to the figure for us to graphically select a learning rate. As the slider is changing the value of the learning rate, we want it to change on the text being displayed. So we use a callback function that accepts LRTXT as a variable for that. But a callback function is usually a function handle, so we need a function that the handle would point to. In this function, we simply update the string property of the LRTXT. Now we add the robot to the environment. We define the initial theta. That's the initial angular state of the robot. We do this by simply creating an instance of the robot using the initial theta we defined. Then we add a plot handle for the target. Now we use a for loop to select different target and animate the robot's responses. First, we get the target graphically and then update the target plot handle. Then, set the loss function handle and compute the current loss value. Now we start a while loop that runs until the loss value reduces below 0.01. In the while loop, we first compute the gradient. Then take a descent direction by reducing the current theta by the learning rate multiple of the gradient. Then compute the loss at this theta, and update the robot. And then re-render the all contents of the figure. Now we have the gradient function, the robot class and the environment setup. It's time to run some tests. To do this, we just run the environment code. and then select target by clicking on any point on the figure. The robot immediately starts moving towards to the target. To increase the rate at which the robot moves towards the target, we increase the learning rate. In some situation, the robot find it difficult to settle at the target when the learning rate is high. In this situation, we reduce the learning rate to allow the robot to settle in on the target. A more robust method would be that can dynamically adjust the learning rate such that it's fast when the robot arm is still far from the target and it slows down to below 1 as the robot nears the target.